G'day guys, welcome to video 2 of the series regarding the student experiment. In this case we're going to talk about modifying an experiment and specifically the language that the syllabus expects you to use, or expects you to be aware of anyway. So the modification, the context says that you need to modify an experiment, and it gives you 3 words for modify. They are refine, redirect, and extend. So you have to do one of these 3 things to an experiment you've previously done, or using a simulation, or an experiment that you've looked up online like we talked about in the previous video. So firstly, let's read what each of these actually say in the syllabus. Now I'm not going to bring them up on the screen. You can get access to the syllabus, remember, and you can find these words in the glossary there. So refine says they all lead with in science to verb. An experiment is to modify the methodology to do something. So I'm just going to skip to that bit at the end. To obtain more accurate or precise data. So I'm going to write those 2 words down. Refine means to find something that is more accurate or more precise. So we need to know what those 2 words mean. Let's have a look at redirect. Redirect, blah, 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 to gain further insight into the phenomena observed in the original experiment. So we need to know, well, what do we mean by further insight? Further insight and phenomena. And finally, for extend, to overcome limitations of the scope or applicability of the data. Scope or oops, I'll just do that over a bit. Applicability. Okay, so we have these 3 words. We need to know what these key ideas actually mean, and then we can talk about what these actually are. So refining, we need to talk about accuracy and precision. So in science, accuracy means that an experiment achieves a value that matches something that is generally accepted. If I was having students measure the value of gravity, I'd expect them to get a value pretty close to 9.8. In chemistry, your magnesium oxide experiment, you'd be expected to get an empirical formula that is pretty close to 1:1 for the formula for MgO. If you were doing, say, something with enzymes in biology, you might be expected to find, oh, the optimal temperature for this enzyme is 37.5 degrees Celsius. So there would be some number or some property that you need to get it that you know is right, because of other reasons, because of literature, and because of that we've done experiments on this before. So your accuracy would be that your methodology allows you to get very close to that result. One of the experiments we did for science is dropping a ball and measuring the timing using a stopwatch and a ruler or a measuring tape to measure the height. This is, it's not a great accuracy because there's a lot of human error involved, and so if my number was around 9.7 or even 9.6, well, I'd say that's pretty good, especially if you're using a stopwatch and a piece of and a slack ruler. But there are other methods that are more accurate. So the big goal for refinement then is, if we make this more accurate, we want to get something that works better. So one way of refining would be to find a different methodology that achieves the same purpose. Okay. So I'm going to put that there. Diff method, same goal. Okay, so maybe you can find an experiment that has a different method to find the same goal. Precision in this case means that you're reducing error. Remember, to be precise means that your spread of your data is now less. And again, a different method will help you do that. That might be as simple as you do the exact same methodology, but you end up using some better equipment. If instead of using a ball and a stopwatch, I used a pair of light gates and a ball bearing so that it's nice and smooth and I don't have to worry about air resistance, or at least not as much air resistance, perhaps I could do that instead. So that would be better precision. Okay, so this one, in my opinion, we'll talk about this a little bit more in terms of easiness, but refinement can be pretty easy to do, but there'll be some difficulties. We'll talk about that. So let's look at redirection. Redirection has two things: further insight and phenomena. Further insight in this case means, well, insight means that you have knowledge inside of about something, that you have a deep knowledge. And so further insight could mean that you are simply just going out and getting better knowledge about something you've observed. The phenomena in this case is your variables, what actual things you are connecting to each other. So in my opinion, you are going to be changing the goal on this one, so you'll have a different goal, but you might have a same or similar or even a different, because it doesn't actually matter, method. And what I mean by this is, if you think back to year 10 when you did the reaction rate experiment, that was a fantastic example of a redirect. You did a prac that was about getting the reactivity of different metals. You used the same method to get the reactivity of calcium carbonate with hydrochloric acid as it related to either a different variable such as molarity or what's the other ones, temperature or surface area. And I kind of like to think of it like this. The original experiment is, what is the effect of A on B when you keep, say, C, D and E controlled? Right? You might then modify it to say, well, what is the effect of B on A? Sorry, not B on A. Let's go D on B. And you keep A, C and E controlled. We're still asking, well, what is the effect of this variable on this same dependent variable, but we're changing what's our controlled and what's our different. We might keep our independent the same and look at how does this affect something else. But remember, there has to be some knowledge that backs up why you've made this change, which is what makes this one a little bit harder than this one to do, but it will make it a little bit easier to justify. Okay? So in this case, the phenomenon, what are our variables? The further insight, we want to see, well, how does something else connect to it? Extension has two words, scope and applicability. Scope in this case means, well, what situation are we applying this to? Right? What is the I don't want to say variables because that's not really right, but how wide can we apply this understanding to it? If, for example, I was to talk about gravity. Now, gravity is a pretty obvious thing on really big scales, even down to human size. We can measure and understand the gravity of, say, two chairs sitting in a room slowly pulling at each other, or pulling at each other with a very weak force. But when we get down to really, really small things like atoms, gravity doesn't make as much sense. It's not quite as or at least our understanding of it isn't quite as deep. So if I was to think about the gravity formula, and there's a formula for gravity, the scope of it is that, well, we kind of need things to be bigger than an atom. If things are smaller than an atom, it gets a little bit fuzzy. So scope in this case is talking about, well, what can we apply the knowledge we've just gained from a previous experiment to? Does it apply to other situations that are similar to it? You don't know. That's what you can look at in terms of extending it. And applicability in this case is whether or not this data actually applies to a different experiment, or if it only applies, or not a different experiment, a different example or a different phenomena. If this only applies to one very certain situation, well, then you can extend your experiment and try to apply it to another situation. I like to sort of think of it as same method, different goal. So the good news is the 10 extension experiment that you did last year, where you had the the chemical reaction rate, that was also kind of an extension, because we didn't turn around and keep the metals the same and just change the molarity. We also changed that variable A from being metals to calcium carbonate. So we applied this methodology to a different goal, that is the investigation of what's what I'm looking for? The investigation of how carbonate, or calcium carbonate specifically, reacted with different molarities of acids, or different temperatures of acids, or different surface areas of tablet reacted with an acid. And that gives us an interesting point here that I think is important to understand. Doesn't have to be just one. You don't get more points for doing multiple. Doesn't have to be one, and you don't need to explain. And what I mean by that is, in your methodology, in your rationale, when you're writing this up, you don't need to turn around and say, this modification to the method is an extension because blah 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 blah. You just need to explain why you're making the change in terms of the theory. Okay, so let's think about, well, which one of these is easiest and which one of these is hardest. I honestly think this is sort of the order that is something that is easiest in order to choose what you're going to change. So to me, refining it in terms of, finding a new method or fixing up some equipment to get better equipment, that's a pretty easy change to do with something. I can look at it and go, well, that was a pretty trash way of doing it. Let's change it to do it with this instead. Instead of using a measuring cylinder, you would maybe use a pipette instead, a volumetric pipette in chemistry. Instead of measuring temperature using a thermometer in a biology experiment, you might measure it using a digital thermometer so that it plots 100 times per second what the temperature is. Instead of using a stopwatch, we might use a light gate for physics. So we make the equipment better. The problem is, though, and this is why I think refinement is then a little bit harder, is that you need to justify why you have done this difference, and you need to link it back to the theory. You need to explain what happened in the original one that prevented you from getting data that requires you to now to make it more a refined process. So I think that's harder to do. I think rationalizing the experimental change is slightly harder to get a good result. So let's have a look at redirect. Redirect in this case, to me, means you need to understand your phenomena. You need to understand your science a bit better to do this. Okay, you need to think about, what are my controlled variables? Do any of these controlled variables have an effect on this if we think about theory? And so what might be a good experiment to go from that? But once you have that redirection plotted out, rationalizing it, writing it into your rationale and explaining it back into connection with theory is pretty easy to do. Extension to me seems a bit the trickiest one, because you need to think of a situation where you can apply the experimental technique you've learnt, with slight changes if you need to a new phenomena that you want to investigate. So to me, extension is the hardest one. Remember, you don't actually get bonus points for trying to do the tricky one, and even saying extension is a tricky one, that's just my perspective in physics. It may very well be in biology that refinement is very, very hard to do and extension is trivial. Excuse me. So sort of take that with a grain of salt, and it's just my perspective thinking about through. Remember, at the end of the day, it doesn't matter what category your modification falls into. You don't have to explain it in extension or redirection. You just have to justify why you're doing that experiment in your rationale in relation to theory. And you need to be able to refer very broadly to the method and the relevant theory about what you expect to happen in general terms. Things like, well, if I keep the surface area of my projectile the same while changing the mass, because it will increase the wind resistance, it will not travel as far when I have a too heavy ball, or because it will reduce the wind resistance or make it harder for wind resistance to push against it or go further. You need to be able to link why you're making this change to some theory in order to get a prediction at the end. Okay, so change must connect to theory in order to get a prediction at the end. Okay, overall you must justify why you're doing this change, okay, and that will probably be the trickier part of it, in explaining it thoroughly in your rationale. Okay, now the next video is going to look at writing a rationale specifically and explaining some of the aspects of it, and then we'll delve into the method. Finally, then we'll look at data presentation, analysis, and evaluation. One thing I do want you to keep in mind: all 3 units have an example of an exemplar version of this experiment, this assignment, that's been provided to us by QCAA. We can let you look at it. I'm going to put the physics one up on the physics page. Miss Malcolm may do the same with the biology, or you may just have to go and ask her to sit down and go through some part of it just to look at an individual piece. But it's very straightforward in that the way that they've done it to achieve a top mark is that they have presented this information, they have talked about the theory, and then they've gone in and gone, well, and this is why this change will connect to this theory to get this prediction at the end. Note, you don't explain what you're going to do to the method so much in terms of how you're doing the change. You just explain what the change is. As an example, if I was to talk about the surface area friction experiment example that I showed you in the previous video, I wouldn't turn around and say stuff like, I'm going to use a inclined plane that fixes at 2-degree angles with a Newton meter at the top to pull on it. I would explain, stuff about free body diagrams and how the force would increase, but I wouldn't actually get down to the nitty-gritty of the methodology. That's for the method itself. Okay. Hope that's helped, and I will see you in the next video. Bye, guys.